So transformations of functions is really pretty simple if we can recognize parent functions or like the graphs of these common functions. So we just played the name that function game. This is a constant function. It's called constant because it never changes. Its range is a single number, but its domain is all real numbers. An identity function, also known as the linear function, okay, especially when it's the linear parent function, that's why it's the identity, returns back something based on a linear set of systems. And if it's just y equal to x, it is the identity because it's the exact same back and forth. Its domain is all real numbers. Its range is all real numbers. The absolute value function looks like a v for value, absolute value. It returns all of the positive numbers, so it's the distance from 0. It looks like a v. We have our standard quadratic function with all real numbers for its domain and everything above 0 for its range. The square root function is one we're going to slow down on for a second. First of all, when we think about square root, there's going to be times, especially because my computer doesn't type a square root symbol very often. Sometimes the things that I use don't actually have a square root symbol. So if you see SQRT, that stands for square root. It is actually the computer latex language for square root. So if any of you are in coding, that is how you get a square root within latex language. Things about square root is that it is taking the square root of a number. Since you cannot take the square root of a negative number without getting an imaginary number, this has a restriction on its domain. Its domain is not all real numbers. It is only from 0 to infinity. You can take the square root of 0, so 0 is included. That means also we have a restricted range, and it's all of the positive values from 0 to infinity. Okay, this is the first one that had a domain that was not all real numbers. For the standard cubic function, domain is all real numbers, range is all real numbers. And then we have our cube root function. The cube root function, kind of like the square root function, doesn't always type pretty on computers. So if you see CBRT, that's standing for cube root as well. So if it's CBRT with stuff inside parentheses afterwards, that's what's underneath the cube root. The radicand there, it just doesn't always type very pretty. But if you notice, for a square root, we had a restriction on our domain. Is there a restriction to a cube root domain? No, its domain is all real numbers still. It goes all the way from the left side to the right side. So the only function on here that we're really dealing with today that has a domain that is not all real numbers is going to be that square root function, because we can't take the square root of a negative number. Do we pretty much recognize these shapes for these functions, especially after playing my game? Yeah, so we're going to be using these graphs of common functions to perform transformations of these different graphs in different ways. Transformations, there's like a whole bunch of things you can do to a graph. And just as a reminder, the sequence of these functions, this is kind of like comes back at the end. You should always perform the transformations in this order. First, start by horizontal shiftings, then any stretches or shrinking, any reflections, and lastly, vertical shifting. So this will come into play if you're combining transformations together, but let's talk about them individually one at a time, and which is all on the other page. We're getting all of them in one. Your vertical shifts, which you may have called vertical translations in classes before this, vertical translations are moving the graph up and down. So my vertical shifts are plus or minuses outside of the function. Okay, when we're vertically translating something or vertically shifting it upwards, that means we're going to take the function and we're going to add a number to the back of it to move it up, or we're going to subtract a number from the back to move it down. We are changing essentially like the beginning value or the y-intercept. That's the easiest place to look at that. But every single output gets shifted up that many units. So if you had 3 dots on a graph, you would shift all of them either up or down the number of units that is C. So if you notice right here, it shows you this, but we might want to highlight it. If we're starting with f of x and we're shifting up, it's moving up. Or we're starting with f of x and we subtract a number, we're moving the entire function down, just shifting it up and down. That is a vertical translation, also called a vertical shift. Same vibe, but opposite direction, we have horizontal shifts. For a horizontal shift, this is when you're going to be moving the graph left or right. This is when you have a plus or a minus sign inside the parentheses or inside the function, underneath the square root, in the denominator, those sorts of things. When it is inside the function and we add or subtract, that's when we're going to move things left and right. If you have a number that you are adding to the function on the inside, that's going to move your graph to the left, which is a little bit backwards, because typically when you think adding numbers, you think adding numbers goes to positive numbers, which is towards the right. But for transformations, because it should be minus c, this is plus a negative, which means we're moving to the left. That's this guy right here, moving it to the left. If you see minus c inside the function, that's when we're moving a function to the right that many units. So every single point you would shift, just counting over the number of points you need to shift it. Okay, horizontal transformations occur inside the function and go the opposite way than you think. Then we have our reflections, and like looking in a mirror and you seeing the opposite, a reflection is going to be how you flip a graph over certain axes. The first one is a reflection about the x-axis, which means flipping over the x-axis. This occurs when you have a negative put in front of the entire function. Is reflected over the x-axis. This is how you get a sad parabola. You make it negative. To reflect something over the y-axis, you're going to take that negative sign and you're going to put it inside the function. So as the input values instead of on the output values. So you plug in a negative x. And that's going to flip it around the y-axis. In a lot of classes, because we were dealing with even functions, reflecting over the y-axis typically doesn't look different. We're not using entirely even functions anymore, so we will actually see a difference in a graph if you reflected about the y-axis. So don't forget about that one. Then we have our vertical stretches and shrinking, and the way that this feels or sounds like is exactly what it is. You're going to take the graph and hold the top and bottom of it. That's vertical. And you're going to either stretch it or shrink it, which means you're going to make it either wider or narrower. For both of these, if you notice, the formula is exactly the same. Where is that number that I'm multiplying by? Is it inside or outside? The c value. Is it inside the function or outside? Outside. So vertical is outside. That makes sense. The only difference is if you have a number that you are multiplying by that is bigger than 0. That should say 1, LOL. Bigger than 1. Can y'all fix my typo, please? That should say 1. If that c value is greater than 1, then the graph is going to be vertically stretched because you're multiplying by a number larger than 1. You're increasing the stretch. You're taking the top and bottom and you're pulling it apart from each other and stretching it by that value c, or you're multiplying all of the outputs by c. If the number you're multiplying by is somewhere between 0 and 1, so a true fraction, not an improper fraction, then that means you are vertically shrinking the graph. You're taking hold of the top and bottom of the function and you're squishing it together or shrinking it together, which means your graph gets wider instead of narrower. But you're multiplying each of its y coordinates by that value c. So if you look here, we have an example of a stretched graph. Take the top and the bottom and you stretch it up and down. Or you have a shrunk graph where you shrink it down. It's the difference between stretching and shrinking on the vertical. And that's when you're multiplying by a number in front of f of x. Our last formula here is horizontal stretches and shrinks. A horizontal stretch and shrink is the same vibe where you're taking, not this time, the sides of the function. What? Oh, yeah.
I don't get how they're like
how they look different?
No, like the equation.
Since they're the same equation? That's a good point. Okay. So yes, they're literally the same equation. What changes here is the type of number you're plugging in.
It's the yeah, okay.
So if this is a Dolly Parton fraction, bigger on top, okay, this is going to stretch the function. So if you multiply by the number 5 or the number 7/2, those are bigger numbers on top. They're greater than 1. It's going to make the graph narrower. You're going to pull the top apart. If you're multiplying by like 1 over 2 or 1 over 5, let's say a JLo fraction, and it's going to shrink the graph. Is that better?
Yeah.
Okay. Thank you for asking a clarifying question. Our last transformation is horizontal stretches and shrinks. So same idea. We're grabbing this time the sides of the function and either shrinking it down or stretching it out. This one is always one that's a little bit confusing, so we slow down. This formula, again, is the same for both stretches and shrinks. They're just called dilations. But if we get particular, and again, a typo, LOL, if C is greater than 1, please fix my typo. So if you have a number that's bigger than 1 multiplied on the inside next to x, the graph is horizontally shrunk. Wow, that word stretched is right there. Mark that out. There's so many typos today. That graph is horizontally shrunk by dividing each of its x coordinates by c. In Algebra 1, you probably learned this, and in Algebra 2, that it was multiplied by their reciprocal. Dividing by c is multiplying by the reciprocal, and I put that down here. It's mathematically equivalent. Dividing by c is mathematically equivalent to multiplying by its reciprocal 1 over c. So this is still what you learned before. Your textbook just uses different phrasing to talk about it. If the number that is inside multiplied by x is between 0 and 1, a JLo fraction, then that means you're horizontally stretching the graph by dividing each of its coordinates by c, or multiplying by 1 over c. So the only one I think that causes a lot of pause is the horizontal stretches and shrinks. The rest of them are pretty straightforward, and they do what we expect them to do. So when you have questions and it asks horizontal stretch and shrink, that's the one I want you to pause at and really take time to think. The rest of them, it's really pretty straightforward with what you do. Now, obviously, there are no examples in these notes because, like I said, it would waste so many trees to print out the number of graphs that you need. So we're going to practice on the whiteboards around here. You have all of the formulas. You have pictures of what's happening to the graphs. I want to see it happen in real time on the whiteboards.